Season 2 is the article writing using HFSS and MATLAB. So MATLAB also we are designing antenna. So first season is the design of microstrip patch antenna. The design of microstrip patch antenna is the basic principle is the transmission line theory. Transmission line theory, the microstrip lines. So everyone knows about the microstrip transmission lines and waveguides. Transmission lines and distribution, particularly here using by the transmission line theory. So here, the concept is a concept of designing microstrip patch antenna by using microstrip line phenomena. That is, it is consists of the 3-layer architecture. It is normally is containing for the 3-layer architecture. So upper layer is a patch. The upper layer is a patch. So patch is going to transmit for the current distribution interacting with the air medium. And here middle layer is a dielectric substrate layer. Dielectric substrate layer. Last layer, the yellow layer is called as a ground plane layer. So the microstrip patch antenna consists of the three layered architecture. First layer is the patch, another layer is the dielectric substrate, third layer is the ground plane. So this is a ground plane substrate layer, and another one is we are giving for the port. Another one is the feed line. We are connecting for the giving for the voltage. Here one voltage supply. Here connecting to the patch. That is called as a feed line. That is the help of feed line. We are giving for the supply for the port to the patch. Another one is a microstrip patch. This is a 3-layered architecture. I show the prototype. So this is one of the microstrip. This is one of the patch antenna. For example, this is a port. The port is interacting for the patch and ground plane. The port is interacting for the patch and ground plane. The upper layer is a patch layer. The bottom layer is a ground plane. So the ground plane, based on the design, we have different classifications there. This is called as a infinite ground plane. So finite ground plane here undergone by the defected ground structure architecture. Defected ground plane architecture. That is a DGS, defected ground surface the architecture. So we are giving for the record design about the ground plane, and middle layer is a substrate layer. This antenna is a rectangular type grid antenna. So the grid antenna is here using by the substrate is here using for the Roger substrate we are using. Roger is a 10.2 dielectric constant we are using. 10.2 dielectric constant we are using. Same Roger material we are using for the all LED monitor also. So this is one of the PhD thesis work. So the one of the PhD thesis work. So why we are not using for the FR4 substrate? So UG students and the PG level studies we are using for the FR4 substrate. FR4 substrate is like as our epoxy glass. So epoxy glass. So we are using for the window material, glass material. That is called as epoxy glass. So epoxy glass, we are how it will be interacting by using by the coupling medium. So upper layer is a positive, another layer is also ground. So upper layer is treated as a positive layer, and the ground layer is treated as a negative layer. In between the layer is a substrate. So wherever the positive lead wire, that is a positive copper is interacting for the ground, we are distribute for the current to interacting with the air medium. That is a concept about the microstrip patch antenna. So the microstrip patch antenna is a 3-layered architecture also there. So here using by the this is a way of the microstrip patch antenna. So this is the height of, we know what is the choose of the frequency, what is your frequency range. Another, what type of material you going to choose, or you going to prepare the prototype. So what is the thickness about the your antenna. The only three things you have you known, and rest of the other. For example, we going to find for the patch length and width. Here L is representing for the length of the patch, W is representing for the width of the patch, and H is representing for the height of the substrate. XL0 is the dielectric constant, and bottom layer is a ground. It is also ground layer also consists of the length and width also. So first you have to know about the what is your operating frequency. You have to choose your own frequency. So your own frequency you have to choose. So while designing microstrip patch anna, first you know the elements. So what is your operating resonant frequency? That is the FR is the resonant frequency or operating frequency. I chosen the operating frequency is at 2.4 gigahertz. 2.4 gigahertz. The antenna able to operate particular 2.4 gigahertz frequency range. Another one is what type of material I am going to choose. So normally top layer and bottom layer both are copper. Top layer and bottom layer both are copper. It having for the 0.05 millimeter thickness or less than or equal to 0.05 millimeter thickness. Bottom and copper layer. It is all these specification is coming from the selection of the substrate. Selection of the substrate, first one is a height. H is a height. That is a height about the thickness. H is the thickness of the substrate material. So I am choosing the substrate is a 1.6 millimeter. So I am choosing the substrate height is a 1.6 millimeter. And here dielectric strength is a XL0R is a 4.4 under epoxy material. I am choosing epoxy version 4 is the choosing material. I show the what are the type of the materials are available. Here up to more than 250 number of materials are available, commercially available in our market. So what is your thickness about antenna? What is the thickness means this is a substrate thickness. So this is called as a height. This is called as a height. Height about the height is a thickness. Thickness like as a thickness of paper. Thickness of the paper. H is called as a height. H is called as a height. So this is a 3 parameter. Only you know the 3 parameter. What is we going to design about your antenna? Only know the 3 parameter. So help of the 3 parameter we going to design the entire combination of the antenna. For example, first you going to find for the 3 layers. So first layer is called as a patch layer. Second layer is called as a substrate. So substrate is already I am given. My specification is a 1.6 thickness and 1.6 thickness. Dielectric constant is a 4.4. So another is a ground plane layer. Ground plane layer. So first you know about the length and width. Here length and width. And what is a feed line? What is the sizes of the feed line? What is the width of the feed line? So what is the length? What is the W? It will be followed by the basic concept about the microstrip transmission line. So Samuel LEO is a textbook. Microwave devices and applications. Microwave devices and applications, Samuel LEO. So it is having separate chapter. Microstrip line, strip line, coplanar line. So coplanar waveguide, all this content is available. So I am choosing the primary topic is a primary mathematical modeling is a microstrip patch. microstrip patch anna. So So the problem is the design of patch anna 2.4 gigahertz. Here quarter wave feed line I preferred. So substrate material 4.4, height is 1.6. It have some procedure, designing procedure. So how to design antenna, I will show the presentation in my laptop. So here before going to design antenna, we know the numbers, what is the length, we don't know. So we going to design such a calculation method. So FR is a 2.4 gigahertz. We are choosing frequency, XL naught R is a 4.4, C is the speed of light, width is equal to C divided by 2 FR square root of XL naught R plus 1 divided by 2. So by using these values, so find for the patch width. That is called as a patch width, and XL naught effective dielectric constant. Again, we have to find. This is a mathematical calculations. These are the mathematical calculation. So here finding for the patch width. Another one is a effective dielectric constant, and we are finding for the effective length and length extension. So after that we are finding for the actual length of the patch. So these are the is not fixed value, sir. We are choosing we are our own specification, we have to choose.
What is the minimum range, what is the maximum range?
Sir, based on the frequency and specification.
How do you relate that frequency?
For example, you want to design for the 4 GHz antenna, but here thickness is a 4.4, means here these values are, by using the calculation, these values are varied.
Suppose I want to calculate the C value some other different way. If any formula is available for relation between FR and C,
FR and C.
in terms of your dimension.
Yes, first we have to know the calculation. By using a calculation, patch, length and width.
For example, frequency 2.5 gigahertz, this is the C value.
Yes.
Suppose I am changing some other.
C is a speed of light. Speed of light. 2.4 is a operating frequency, resonant frequency.
Okay.
So speed of light is a common one, 3 into 10 to the power of 8 meter per second. That is a fixed value. So here speed of light, that is a C is the speed of light. F is a resonant frequency. The antenna is able to use for the resonant frequency. This is a 8 GHz antenna. So length and width also we are having for the different length and width. So by using the calculation, we find for the length and width about the patch. So after that we are finding for the, is a simple calculation only. So this is my especially calculation, mathematical calculation is a similar one. So this calculation is available somewhere Leo textbook. That is a PH publication. Here frequency is our own frequency, we going to select. Specification also, what type of material we are using, either using for the BDMS structure, polythene structure, or everything Kapton material. So different material, we have different specification also there. Based on the specification, we going to design for the patch length and width. Again you have to find for the ground plane length and width. So I am calculating for the ground plane actual length, patch, and here using for the length of the substrate, total length of the substrate, height and feed lines. So all those information I am calculating by using the existing the phenomena about the microstrip patch antenna. So while I am writing the article for design of microstrip patch antenna for some other application, first I am going to justify where I am taken from the mathematical phenomena. So same mathematical phenomena I am taken from the textbook and some Colin or Samuel Leo or some other textbook. So I going to justify what is our designing antenna. Mathematically proven concept. So what is the length and width and width about the patch and ground plane. So this is the idea for first we are designing for the what is the coordinate value, what is the length and width, all those information you going to design by mathematical phenomena. After that you have to start the simulation. Next you are going to start the simulation because the antenna is already I told antenna is one of the conductor. If you given a particular voltage, it is a distribute for the some current, some leakage of energy in the air medium. So you going to design any type of antenna without no unknowing dimensional, it also propagating. That is one of the way of approach to justified for the length and width, what is your operating frequency, what is your specification, all those information is essentially required. That's why I am giving for the mathematical phenomena. Next step I am going to design a microstrip patch antenna. So I am having for the simulator tool. So normally I am using electronic desktop simulator. So this is the electronic desktop simulator ANSYS 2020 R1 version. So I told for this is a microstrip patch antenna. This is a patch, the feed line, the edge of the port, and another one is a ground plane. Here thickness is the substrate material. All those things we going to design how it will be established for the achieved for the this kind of specification. I show the demonstration. I will give for the step by step. First. First, I choosing a new model. So the new model you have to rename about the test 1. So I rename as a test 1. Double click on this model. So insert the one new HFSS design. Insert the HFSS design. One new design is there. New design is there. Here this is a design terminology, 3D components and models and circuit elements. Same antenna, the antenna is a passive antenna. Same antenna it will be used for the active antenna, active sources also. So that is called as a reconfigured antenna. That is antenna also. That antenna also we are using for the same toolbox also possible. And the circuit elements, here boundary conditions and excitation, supply voltage, and here mesh analysis, here using for the optimizer, and another one is the result, here using far field component and radiation also there. This is a workplace. So first of all I am going to design for the patch antenna. So first layer is a patch layer. First layer is so I am going to design for the one of the layer. So this layer is I draw anywhere in the work table. I draw the rectangular. First rectangular one. So right click of the rectangular one. I renamed as first I drawn the last layer ground plane I am going to draw. So first ground plane and here choosing for the layer is a XY plane. I am choosing the plane is the boundary is a XY plane. Here using the positions, I already using for the same calculation. I derive the positions, and here length is a 60 by 60. The length is a 60 by 60. So I fit to all. We are making as a ground plane layer. First layer is a ground plane layer. So second layer is a, so I am using by this substrate layer. Substrate layer I am going to design by using by the cuboid shape, that is called as a box shape. So substrate anywhere here you have to draw the box, that is called as a substrate. So this is a, you have to give a rename. Rename is a FR4 substrate. So here material, what type of material we are using? Here edit option also there. Click on the edit option. Here so here giving for the variety of the substrate is available. So these substrate are system library sources. For example, here research oriented means we are using for the Roger, we are using Roger here using for the Roger Durite. Here using for the Roger material also there. This is a LCD PCB component, but I am using for the FR4 also. Here type on the FR4. Here variety of the FR4 epoxy is there. Here relative permeability, that is called as XL0 R. I choosing the XL0 R is a 4.4. My material specification is a 4.4. My material specification is a 4.4. So here FR4 epoxy, here 4.4, and here relative permeability is a 4.4 is the chosen one. You click on this one. And here giving for the apply and OK. So next I am going to modify about the dimensional length and width and height. So here dimensional, here create the box is there. Here one more dimensional also there. So here positions x, y, z, that is the Cartesian coordination. We going to find for the Cartesian formula. So here thickness is a 60 by 60, 1.6. So here patch length, ground plane length is a 60 by 60. Here patch length is a 60 by 60. Patch is a 60 by 60, and substrate is a FR4. Sorry, is not a, first we are designed for the ground plane. First layer is a ground plane, second layer is a FR4. Here 4.4 is FR4, 60 cross 60. I am using for the 1.6 thickness. 1.6 thickness. So my material specification is a 1.6. So here how I am giving for the 1.6 is the, here length is a 60 and 60, and another more height also we are giving for the height also 1.6. Height also 1.6. Such I drawn in the simulator. So the patch ground plane is a 60 by 60 millimeter. And here also 60 by 60 millimeter, but the height is a 1.6. My material configuration is drawn in the simulator software. You have any doubts for designing for the ground plane and substrate? So next I am going to design for the patch layer. So the patch layer is a, so simply here draw the any rectangular box. So you have to give for the rename. You rename as a patch. Rename is a patch, and here using by the dimensional. So here dimensional is a I using by the Cartesian, same Cartesian coordinate. So 1.6 is the thickness. Above the thickness is the patch is the top layer. So length of the patch is 29.4. Here width is 38. We are giving for the apply and OK. So this line is indicate for the patch. This line is drawing is indicate for the patch, and here indicate for the ground plane, and here FR4 is a thickness. So if you want to differentiate, we are using for the different color coding in the properties. So I am using for the, if you want to change different color coding, we are going to change different color coding in the properties also. You want to differentiate for the values, differentiate the layers, so the blue layer is indicate, navy blue layer is indicate for the substrate layer, the patch layer is indicate here, this is a patch layer, ground plane layer is indicate here, this is a ground plane. So 3 layered architecture I drawn in the software. So next step is I'm going to design for the feed lines. So I'm going to design for the feed lines. This is called as a feed line. This is a feed line. The feed line I am going to design. The feed line is interacting with respect to patch and port. The fourth step is designing for the feed line. The feed line is interacting patch and port, excitation port. So how to design a feed line? So again I draw the rectangular. I change properties is a rename as a rectangular by the feed line, line 1. So I am giving for the feed line 1 on feed line 2. I will show the differentiation. So next is a so this is a feed line. So this is a feed line. The feed line interacting with respect to patch. So almost the step is completed, but this line is interacting, separately interacting with respect to feed line. Again draw the one more block that is called as a feed line 2. That is why I am written feed line 2. Later I will tell you. (14.7) minus 2.5, and above the thickness is a 1.6. Here length is a minus 9.5. and here 5. So another one more feed line is I placed on the in between the feed line 2, placed in between feed line 1 and patch. Why I am placed inside of this design is the feed line merged with patch. Such a way we are connecting the tool is a feed line 2. So how it will be interacting merged with patch feed line 1 merged with the patch via feed line 2 by using a Boolean operator. So here Boolean operation also there. So click on the feed line 2 on the patch. Click on the feed line 2 on patch. So if you go for these are the Boolean operator, that is a unite, and another one is a substrate, interrupt, another one is a spread and imprint. This operator also there. I choose on the substrate operator. Here having for the one in this pop-up window here having for the blank parts and tool parts is also there. So the blank part is a patch. So this is the way of we are connecting the feed line 1 and patch. So here patch and feed line are using for the another Boolean operator unite. So you click on the unite, both the structure is the union together. So this is so you show all the operations are coming this model analyzing tool. So everyone you click on all those, insert the plane, we are changing the values, all those information you are notified in this toolbox. So what is doing? So you have to find this toolbox, you know about the simulation process. So first you have to know what type of material and what is a patch and what is a ground plane, and another one is we are using Boolean operation, feed line 2 interacting with respect to patch, that is a substrate. So we are getting for the patch and feed line 1 we are giving for the unite operation also there. So this is a 3 layer drawn in the we are drawing in the simulator toolbox. First is a ground layer, substrate layer, patch layer. Additionally, we are drawn. I completed for the feed line structure also. Next, I am giving for the port. Virtually, I connecting for the port. So, patch and ground plane both are we are having for the some connectivity is a port is there. So I draw the port I using by the simulator tool. So next I am selecting for the this is a XY plane, but the port is I am using for the YZ plane. YZ plane. Simply here choosing for the here XY and YZ plane. So draw the single rectangular. Here rename is the edge. Rename is the edge, and here giving for the properties. So here listen. So listen all of you. So the excitation port I drawn. The excitation port is provide for the supply voltage between for the ground plane and patch. So normally we are giving for the 1 volt supply. Practically the port is fabricated by SMA connector, surface mount adapter. So that is one of the surface mount adapter. So surface mount adapter, it is having for the four positive pins and one negative pin. So we are middle pin is a positive and rest of the pins also having for the negative pins. So this is a surface. So I show the connector. So this is a So this is a connector. The central pin is a positive. Rest of the pins, fours are the negative pin. Central pin is interacting on the feed line of the microstrip patch, and rest of the ground four pins interacting on the ground plane. So this is a positive pin, and the last two pins are the negative pin. We are omitting for the first two pins. So this is the concept we are designing for the edge connector. This is the concept we are designing for the edge connector. So next is we are assigning for the excitation boundary. So excitation boundary. So here using for the thermal network. We going to using a solution type is a modular solution type, because it is a driven model. So here using for the click on the edge save. You are assigning for the excitation. The excitation is assigning for the port. The port is going to assign for the lump. It have a 4 port is also there. Circuit port. Another one is a floated port. Another one is a lumped port. Wave port also there. So I click on this kind of the port is a lumped port. So I click on the lumped port. So microstrip patch and having for the impedance matching is a 50 ohm impedance matching. So I giving for the 50 ohm. So the port number is a source. Port number is a source. So here using for the new line is a drawn the edge connector. So this is a first you drawn the new line. So the new line is a drawn from the ground plane to patch. The new line is drawn from the ground plane to patch. The patch arrow mark is drawn from the ground plane to top layer. If beyond the top layer, it is a disconnected one. Such a way I am again to retry reconnectivity. Because it is shown for the invalid. First draw the port, then only we are analyzing the simulation. Vamos a ver.